Welcome to this lecture on semiconductors. In this lecture, I'm going to discuss some of the fundamental aspects of semiconductors and its applications. Okay. What are semiconductors? Semiconductors are materials which have band gap. Okay, EG is the standard notation we use for band gap. If the band gap is less than 3 electron volt, then we call those materials as semiconductors. Okay, so materials for which band gap less than 3 electron volt, those materials we call as semiconductors. Right, what is meant by band gap? In the EK diagram, okay, as per reduced zone scheme, right, so if we plot energy, and this is the conduction band and this is the valence band. Okay, so this is conduction band and this is valence band. So this is k-axis. Okay, so this diagram is the EK diagram, and here the energy correspond to the bottom of the conduction band. Okay, the bottom of the conduction band is represented as EC, and the energy correspond to the top of the valence band is represented as EV. Okay, so EC is the energy correspond to bottom of the conduction band, and EV correspond to the energy of the top of the valence band. The energy difference between these two is what we call as band gap, EG. Okay, so for a material, if the band gap is less than 3 electron volt, we call those materials as semiconductors. Okay, then in semiconductors, we classify semiconductors basically into two. Okay, so classification. There are different ways of classifying semiconductors. Okay, this is one of the way. We classify semiconductors into two. One is intrinsic semiconductor. The other one is extrinsic semiconductor. Okay, intrinsic semiconductor means pure semiconductor, that is without adding any impurity. You take the host crystal or you take the pure crystal. The pure crystal of the material will act as a semiconductor. Extrinsic semiconductor means we add some impurity to some crystals so that we can increase the carrier concentration. Okay, so here we add some impurity to the impurity is added to some crystals so that the carrier concentration, okay, get increased. We call those semiconductors as extrinsic semiconductor. Okay, and this EK diagram will give you the idea about valence band and conduction band in reciprocal space, right? But normally we draw this valence band like a box. Okay, we represent like box notation, and we say that this is valence band and this is what we call as conduction band. Okay, we represent usually like this. Okay, this is notation in real space. This is the notation in reciprocal space. Okay, why I am telling reciprocal space? Because you know very well K is nothing but 2 pi by lambda. Lambda is the wavelength. Since wavelength is in the denominator, so K is called reciprocal. So the unit of K is the reciprocal of length. Okay, so this diagram correspond to the reciprocal space, right? Yeah. Now this energy is the EV, top of the valence band, and this energy is the EC, bottom of the conduction band. And this energy, okay, this energy is actually EC plus chi, where chi is the electron affinity of the material. Okay, what is chi? Chi is electron affinity of the material. Electron affinity. Okay, yeah. Now, so this is the basic idea about this EK diagram, and this is an introduction to semiconductors. Okay, so semiconductors are materials for which band gap will be less than 3 electron volt. That's the basic point you should keep in mind. And we classify semiconductors into two: intrinsic and extrinsic semiconductor. What I'm going to do, first I'm going to focus on intrinsic semiconductors. Okay, then we'll discuss about extrinsic semiconductor. Right. Now, intrinsic semiconductor. As I told you before, intrinsic semiconductor means pure semiconductor. Okay, that is without adding any impurity, right? In intrinsic semiconductor, okay, before going to discuss intrinsic, let me give this point. In intrinsic semiconductor, we classify intrinsic semiconductor into two, right? One is elemental semiconductor, the other one is compound semiconductor. Elemental semiconductor and the other one compound semiconductor. In the periodic table, okay, elements belong to group 14, right? This group, the old symbol for this group is group 4A. Group 4A. So elements belong to group 4A, very specifically silicon and germanium. Okay, their band gaps are less than 3 electron volt. So these materials, okay, are called intrinsic semiconductors, elemental, right? They are elemental intrinsic semiconductors. Okay, in compound semiconductor we have, so remember, for elemental semiconductor, silicon and germanium are very good examples. Okay, the band gap of silicon is 1.1 electron volt and the band gap of germanium is 0.67 electron volt. Okay, both of them have value less than 3 electron volt, so they are elemental examples for elemental semiconductors. In compound semiconductor we have binary compound semiconductor, we have ternary compound semiconductor, quaternary compound semiconductors. Okay, so binary, then we have ternary compound semiconductor, then we have quaternary compound semiconductor, etc., etc. Binary means, see, the word itself clearly suggests that you have to take two elements and you have to mix it. Okay, here you have to form a compound, right? It's not just a mixture. You take two different elements, okay, combine them and form a compound. That binary compound, okay, it is a pure crystal that will act as a semiconductor. Okay, so in binary compound semiconductor, group 12, right, that is the old name is 2B, and group 16, the old name is 6A. The elements belong to group 12 and group 16. Okay, when they combine, they'll form binary compounds, and those binary compounds act as a intrinsic semiconductor. For example, in group 12 we have elements like zinc, cadmium, mercury. Okay, and in group 16 we have element oxygen, sulfur, selenium, tellurium, polonium. Okay, now if I combine cadmium with the selenium, okay, I'll get what is called cadmium selenide. Cadmium selenide cadmium selenide is a nice example for compound semiconductor. Here we are taking one element from group 2b and another element from group 6a. So these compound semiconductors are called 2,6 compound semiconductors. So these are all called, these compound semiconductors are called 2,6 compound semiconductors. Okay, 2,6. Similarly, we can take elements from group 13 of the modern periodic table. The old name is group 3a. Okay, similarly, element from group 15, also called 5a. Right? In group 13, we have elements like boron, aluminium, gallium, indium, thallium. Okay, and in group 15 we have nitrogen, phosphorus, arsenic, antimony, bismuth, etc. Right? You take any one element from this and any one element from this, okay, and form a compound. If that compound has band gap less than 3 electron volt, then we can call them as intrinsic semiconductor. Okay, and here we have plenty of examples. Suppose you take gallium and combine with arsenic, you will get a compound called gallium arsenide. Gallium arsenide is a very famous example for intrinsic semiconductor. Okay, it has band gap 1.42 electron volt, okay, which is less than 3. Right? So, and these semiconductors, by combining one element from group 13 and another element from group 15, if you get a semiconductor, we call that semiconductor as 3,5 semiconductor. I'm sorry, 3,5 semiconductor. So in binary compound, we have 2,6 compound semiconductor and we have 3,5 compound semiconductors. Okay, so here by combining two elements, we are forming a compound, pure compound. So it is a pure material, and that pure material have band gap less than 3 electron volt. So we call them as semiconductors. Okay, then we also have ternary compounds. In ternary compound semiconductor, what we'll do is we'll take two elements from group 13. So from group 13 we have boron, aluminium, gallium, okay, indium, and you take one element from group 15. Say in group 15 we have nitrogen, phosphorus, arsenic, antimony, etc. Okay, now what I'm going to do, I'm going to take two elements in group 13. Say for example, I'll take aluminium and gallium. Okay, then I'll combine these two with an element from group 15, that is arsenic. So if I combine these three, I'll get a compound called aluminium gallium arsenide. Okay, aluminium gallium arsenide. Actually, how we prepare this compound is we'll take gallium arsenide, pure gallium arsenide. In this, we remove some number of gallium atoms and we'll replace it by aluminium. Okay, some number of gallium atoms are replaced by aluminium, so you'll get aluminium gallium arsenide. So the formula of aluminium gallium arsenide is, if aluminium has X fraction in the material, then gallium is supposed to have 1 minus X fraction. Okay, so this is the standard notation for aluminium gallium arsenide, standard formula. Okay, people call this simply as AlGaAs. AlGaAs is the very famous intrinsic semiconductor. Okay, and what is the advantage here is that for in AlGaAs, band gap depends on the value of X. So as the X changes, band gap changes. Whereas in the other materials, okay, in binary compounds, right, and in elemental semiconductor, here band gap is a fixed value. Okay, you cannot alter the band gap. Whereas in AlGaAs, okay, as you vary the value of X, right, the band gap changes. Okay, this is an added advantage, okay, to understand some of the applications, or you can make use of this, right, for some application purpose. Okay, we are going to discuss as we go along, right? Yeah. So this is what we call as ternary compound semiconductor. We also have quaternary compound semiconductors, but this is the basic idea. So you can understand, right, how quaternary compound semiconductors will work. Now, apart from this classification, okay, we have elemental, we have compound semiconductors. Apart from this, we also classify semiconductors. We also classify semiconductors into two, okay, based on whether the material has whether the semiconductor has direct band gap or indirect band gap. So the next classification is direct band gap semiconductors and indirect band gap semiconductors. Direct band gap semiconductor and indirect band gap semiconductor. See, here I am going to take intrinsic semiconductors only, because our focus is in this lecture we are going to focus mainly on intrinsic semiconductor. Once we complete intrinsic semiconductor, we will discuss extrinsic. Okay, so in intrinsic semiconductor we have two types. Okay, this is another way of classifying intrinsic direct band gap semiconductor and indirect band gap semiconductor. What is meant by direct band gap and what is meant by indirect band gap? Okay, before going to discuss this, let me make a point here. That is, almost all semiconductors have both direct band gap and indirect band gap. So almost all semiconductors have both direct band gap and indirect band gap. Okay, then how to identify whether a semiconductor is a direct band gap semiconductor or indirect band gap semiconductor? What we do is we'll first find out what's the band gap for direct, what's the direct band gap, and we'll find out what's the indirect band gap for a given material or a given semiconductor. Then among these, which one is low? The lower value decides the material. Okay, suppose if the direct band gap is low, we call that semiconductor as direct band gap semiconductor. If indirect band gap is low, then we call the material as indirect band gap semiconductor. Okay, see, what I'm trying to say is that suppose in the E versus K diagram, right? Suppose I have a band here and another band here. Okay, and this is the valence band, right? So here for this band, this is the lowest bottom energy, which is EC, and for this band, this is the valence band, so this is the EV, and this gap is the band gap. And here, see, the bottom of the conduction band and the top of the valence band both exist in the same K value. This is energy axis, this is K axis. So K values for this bottom and the top are same. Okay, suppose in a band, or if the bottom of the conduction band and top of the valence band have same K value, we call that band gap as direct band gap. This is direct. Now I have another band here. Okay, now I'll measure the band gap of these two. Okay, this is the top of the valence band and this is the bottom of this band. Now this band has a different K value, correct? This K value is different and this K value is different. So the top of valence band and the bottom of this band, they are different. Therefore, this band gap is called indirect band gap. I'm sorry, it is called indirect. So most semiconductors, almost all semiconductors have both direct band gap and indirect band gap. Then how to identify whether it is direct or indirect? Okay, see the band gap value, right? If so, in this case, this band gap is low compared to this band gap. Therefore, this material is called direct band gap semiconductor. Okay. In some other case, you may also get like this information. That is, let me draw and show you. Suppose in some material we have a band gap like this. In some material, right? So this is the top of the valence band, and this is the bottom of this band. Okay, let me call this as EC and this is EV. Now this gap is EG, and this is, see here, this K value is different. Okay, bottom of this is different and top of this is different. Okay, they have different K value. So this band gap is the indirect band gap. What about this one? This is the direct band gap. Now in this material, indirect band gap have lower value compared to direct. Therefore, this material is called indirect band gap semiconductor. Okay, what you have to do is just to see the bottom of the conduction band and top of the valence band. If they exist in the same K value, it is direct. If they exist in different K value, okay, this is the K axis. See, this is the K value for this band and this is the K value for this band. They are different. Therefore, this type of semiconductors are called indirect band gap semiconductor. Okay, now I'll give some examples for direct band gap semiconductors and indirect band gap semiconductors. Okay, direct band gap semiconductors and indirect band gap semiconductors. Okay, keep this in mind. Direct band gap semiconductors, okay, are very useful in the optoelectronic studies, right? Because when electrons move from conduction band to valence band, okay, the energy is released predominantly as photons. Okay, whereas in indirect band, when so we have direct band gap semiconductor and indirect band gap semiconductor. Okay, I'll give examples for direct band gap semiconductors gallium arsenide, indium phosphide, indium stibide, then gallium stibide, okay, indium nitride, okay, and the band gap values are gallium arsenide 1.42 electron volt. For indium phosphide the value is 1.35 electron volt, and for indium stibide it is 0.17 electron volt. For gallium stibide it is 0.73 electron volt, and indium nitride the value is 0.65 electron volt. We have many examples. Here I have given only few, right? Keep this in mind. In direct band gap semiconductor, okay, the bottom of the conduction band and the top of the valence band have same K value, okay, and here when electron undergoes transition from conduction band to valence band, when electron undergo transition from conduction band to valence band, energy is released predominantly as photons. Energy is released predominantly as photons, okay. So this is very useful in the case of optoelectronic applications, okay. Then similarly in the case of indirect band gap semiconductor, yes, we have plenty of examples: germanium, silicon, aluminum stibide, aluminum arsenide, gallium phosphide, aluminum phosphide, silicon carbide. Yeah, these are all examples for indirect band gap semiconductors, and the band gap value for germanium it is 0.67 electron volt, okay. All these values are in electron volt. Silicon it is 1.1 electron volt. Aluminum stibide it is 1.58 electron volt. Aluminum arsenide it is 2.16 electron volt, okay. Gallium phosphide 2.26 electron volt, aluminum phosphide 2.45 electron volt, and silicon carbide it is 2.42 electron volt. And we have many examples, okay. I have given few only here, right? All these values are in electron volt, right? And remember, in the case of indirect band gap semiconductor, when electrons undergo transition from conduction band to valence band, okay, the excess energy is released predominantly as heat, okay. The excess energy is released predominantly as heat. So indirect band gap semiconductors, okay, they are not the usual materials for optoelectronic applications, right? Yeah, we are using for some purpose, but in general indirect band gap semiconductors are not very much useful for optoelectronic applications, okay, right. I stop here. We'll continue this lecture in the next class, and I'll introduce what are all the carriers, right, which are available in the conduction band and valence band, right, and how the concentration of carrier changes as the temperature changes, okay, and we'll discuss about the conductivity and other things in the next lecture, okay. I stop here. Thank you.